Thank you. So this morning, I will now talk about the local aspects of the program, but let me first recall the general setting that we had yesterday. So X is a G variety, which is quasi-affine spherical. And here we'll take K to be a local field. And to simplify life, I will assume that the characteristic of K is 0. And as yesterday, actually, we can restrict for this morning to the homogeneous case, so G mod H. And also a simplification assumption, so we'll assume, to simplify, that when you take the K points of X, it has a GK invariant measure that we will fix also implicitly, so that we'll be able to identify everything with functions. So namely, I don't have to distinguish between measures or half densities, and everything will just be functions. And let me now remind you of the main construction of yesterday. So I very quickly explained at the very end how to associate to X a dual group, or even an L group, actually. So provided no type N root, which also I will assume implicitly in what follows, as well as a morphism iota X from this dual group times a copy of SL2 to the L group of G. And the yoga of this morning will be that this dual group, together with this morphism, should control much, or some sense, of the spectra of X locally. So let me start with an example, and it's to answer Yannis' question from yesterday, which is the group case. So let me illustrate this morphism in the group case and what the conjecture should say in this particular situation. So let me recall the group case is where the space X is the group itself, and G is two copies of H acting by left and right translation. And as I badly explained yesterday, so let me re-explain it this way. So we have canonical carton associated to X, and its dual carton is naturally mapping to the dual carton of G, which in this case is just a product of two copies of the canonical carton of H. And I said last time that this one can also be identified with the dual carton of H, which is good because X is just H. And that this morphism is not the obvious one, it's not the diagonal, but it's slightly twisted. So it's sending an element A here to A in the first copy, and the conjugate by the longest element in the Y group of A inverse in the second copy, so WL. In the Y group of H. Okay. And also we have the set of simple roots, simple spherical roots of X. And as I said, so yesterday, this is a sum alpha 1 plus minus, or WL alpha, or let me write it like this, for alpha a simple root of H, where this is identified. So this is really a sum of alpha in the first copy and this other root, which might or might not be equal to alpha in the second copy. And then, okay, you have to extend this morphism to a morphism between dual groups, right? And the dual group of X, since it has the same root system as H, it's just the dual group of H. The dual group of G is just the product of two copies of the dual group of H. And if you apply the recipe I gave yesterday, actually what you find is the following morphism, which is not, again, the natural one, it's not the diagonal, but it's the identity. I mean, it can already be seen on at the level of maximal tori, It's the identity in the first variable. And the second variable, it's a certain automorphism, actually an evolution, doing this on a maximal torus and acting like this on simple roots. So it's called Chovale Automorphism. So let me define this. Well, C is the Chovale. For the moment, it's just a Chovale automorphism. I will explain why. Which is so preserving the Borel pair. So recall that this group is coming with a pinning, but for the moment we don't ask C to fix the pinning because, as I said yesterday, the condition about this morphism just characterize it up to conjugacy by the maximal torus, so it will not fix the pinning a priori. And acting, so C of an element in the maximal torus is what you see here. So that's one thing. And then I said at the very end that actually Knop has proposed a better normalization of that morphism that makes it unique up to conjugacy by the maximal tori of the dual group of X, right? And in this case, what you get is a particular Chovale automorphism. So, and actually, you don't get the one which is preserving the pinning, but the one that has to send the pinning. So this is the pinning to its opposite, where you just multiply by -1 each elements in the basis elements of the root spaces. So example is when H is GLN. This particular choice of the Chovale isomorphism, and by the way, this choice of the Chovale automorphism gives you an involution, it's easy to see, is sending an element G in GLNC, which is the dual group, to W transpose G inverse W, where W is the permutation matrix representing the longest element in the val group, as you can check. Okay, and just to finish this example, what should the local conjecture in this case should basically say that a representation pi, irreducible representation of G, is X distinguished if and only if its Langlands parameter factors through the morphism between dual groups. And let me make this concrete. So what's an irreducible representation of G? So G is a product of two copies of H, so it's a tensor product of two irreducible representation of H, one for each copy, right? And the Langlands parameter of pi is just the product of the Langlands parameter of sigma 1 and sigma 2. And now it's easy to translate each of the two sides of the equivalence, like being X distinguished in this case means that you have a H invariant linear form, where H is this time the kernel, the stabilizer of a one point in X, that is the diagonal copy of H. So pi is X distinguished means that there is an invariant pairing between sigma 1 and sigma 2. So that is sigma 2 is isomorphic to sigma 1 contragradient. And the condition that it factors through this morphism, right, just means that the Langlands parameter of sigma 2 is the compose of the Langlands parameter of sigma 1 by the Chovale automorphism, which is a well-known fact for the local Langlands correspondence for GLN, which is just saying that the Langlands parameter of a contragradient representation is the contragradient Langlands parameter. And under this form, this conjecture is known in some cases. So for classical groups over periodic fields, this was proved by Tachot using the endoscopic characterization. And for real groups, this was proved by Adams and Vaughan. Right. Okay. Okay. But this is basically.
What do you mean by now? So, and if you have the parameters, then you get this constructor.
Yes.
So if you admit, say, Langlands correspondence.
If you admit Langlands correspondence, so we have Langlands correspondence for real groups, and we have the Langlands correspondence for classical groups, at least in the quasi-split case of a p-adic field.
But if you admit it, then you can prove it, or?
Yes. So again, it's proved using endoscopy.
Sorry? I only think you can get this direction, not this. Like, you can. It's actually distinguished.
Yes, yeah, okay. It's yeah, you okay. It's at the level of packets. So yeah, let me say it's yeah, it's not an equivalence, right? Yeah, there is a problem when you have packet sets, so we'll talk about it.
Already in the group case, right?
Yeah, it's the group cases. Yeah. So sorry. Yeah, it was a bit. Yeah, it was two approximative statements. Sorry. But if you consider packets, it's fine. So modulo stability issues. Okay, so now let me move to one of the main topics of this morning, which are so. The goal will be to state some precise local conjectures, and as you will see, they are of different flavor. And we don't have yet a unified statement, even conjecturally. So the first statement I would like to, the first conjecture I would like to state has to do with the decomposition of the L2 space. And so for this, I will have to give a very quick reminder on what it means to decompose a unitary representation, and more precisely about Plancherel decompositions. And I will follow a very nice description of those due to Bernstein. And so the goal is to give just a concrete meaning. So sometimes you see something like this. So you have the L2 space. As I say, so we fix the invariant measure. So this is just a L2 space square integrable functions. And this is a unitary representation of G. And we would like to write a direct integral decomposition of this. So indexed by some set that I will call capital Phi, and we'll see later why, of some unitary representation P Phi times a measure. Okay, so it's a very suggestive notation, but let me explain slightly more precisely what it means. So the idea, that was explained very nicely in the paper of Bernstein, is that to make this concrete, you have to pass to a nice subspace, which is, for example, the Schwarz space. So space of smooth compactly supported functions. And in this case, following decomposition amounts to the following set of data. So first, well, you need, of course, a measured space. Then some assignment, sending an element phi in capital Phi to some unitary representation here that are actually going to be discretely and in finite pieces, decomposable discretely in finite pieces. So let me write this way. Okay, so a priori, discretely decomposable, let's say. This way, where unit G is the unitary dual of G. So this is a set of isomorphism classes of unitary representations, where MP phi is the multiplicity, so it can be any integer or maybe infinity, but still it's the discretely decomposable representation. And we would like this to be measurable in some sense. Let me not worry about it. And third and last one is another map which sends an element in our parameter space to what I will denote by G phi, which is, so it's going to be semi-positive, G invariant semi-positive. Scalar product with a certain property, well, basically such that let me say it in a nutshell here, and then I will write more precisely on the other board. Such that, so when you have a semi-positive scalar product, you can always complete your space with respect to this, the corresponding Hilbert norm, and get a unitary representation. And it should be isomorphic to this one, right? And also, if you want to be very careful, you have to ask some linear independence between this G phi, because you don't want to do. So let's ask them to be linearly independent. And then now I will rewrite these conditions slightly differently. Or equivalently, G phi, so you can look at it as some map from the tensor product to C, which is linear in the first variable and semi-linear in the second variable. It should factor through, I mean, there is a map to the completion, right? And then here you can take the invariant scalar product on this unitary representation. So this is another way to state this condition. But this map is surjective if you take smooth vectors. Okay, such that, and now the main condition is that this should give you a decomposition of the L2 space, but we will formulate this decomposition in terms of scalar products, simply, such that for all F1 and F2 in the Schwarz space of X, the L2 scalar product of F1 and F2 is the integral of a phi of this semi-positive, semi-definite scalar products. And very, I mean, broadly, this decomposition is obtained from this equality by completing on both sides. Okay. So let me make now a series of remarks. So the first remark is that you can always replace this data. So this is a triple phi d mu and a family of scalar products for the moment. So I will get them in 1 moment by the same parameter space, but then you multiply the measure by some function and you divide the scalar product by the same function, where kappa is, let's say, from phi to positive real numbers, and it's measurable. So it's obvious because somehow what's canonical here is only the product of the scalar products with the measure. So it's really, I just want to emphasize that a priori, the measure is not uniquely defined, but only its class. And even so, I mean, but this is the only ambiguity when you want a canonical decomposition like this. So up to this decomposition, I mean, is unique when you take for phi the unitary dual of G, and P phi is a direct sum of copies of phi, right? And this is called the Plancherel decomposition, because you are really, it corresponds to the decomposition in isotypic components in some sense. And I will give you an example in the group case in 1 moment. And the third one is that G phi is called a relative character. And this is a notion that you already saw in Pierre-Henri's talks. So I will explain 1 moment the relation. But let me first explain why it's called a relative character. So by looking at the group case. So in the group case, so it's again the space is H and the group G is 2 copies of H.
We take the parent to be bilinear, right? So
No. If it's okay.
Right? So when you write F1, F2, L2, you would.
No, it's Hermitian. Hermitian, and here, it's a Schubert bar, maybe you prefer. But I will not bother putting complex conjugation everywhere, but yes. So in the group case, P phi is, I mean, assuming that P phi is irreducible. So as we saw at the beginning, the representations that are X distinguished are of the form a representation tensor. It's a contragradient, and these are the only kind of representations that can appear in the Plancherel decomposition as well. And let's assume that P phi is just one of those, so it's not a direct sum, to simplify. So where sigma is irreducible. And in this case, it's relatively easy to show that up to scalar, this relative character, so it's up to scalar, let me put it out here, because as I said, everything is normalized up to scalar. It's the trace of pi of sigma f1 and sigma f2 adjoint, or in other words, it's just the Hilbert-Schmidt scalar product of these two operators. But you see that you recover the trace, so why it's called relative characters. And then there's, so in the general case, well, I will assume to simplify, so that x of k is homogeneous, but with suitable modifications, you have something similar in general. So I just want to relate these relative characters to the h times h invariant distributions that appeared in Pierre Henry's talks. So this is the relative character as written above. Now what you can do is that x is g mod h, right? So you can just lift those functions to functions on G, where this map is just integral over h times h, showing both copies. And this is, after all, G invariant for the diagonal action of G. So this means that this pairing will factor through the convolution product, essentially. Right? And there you get the following. So you can go to, let's say, okay, I'll write it like this maybe. The tensor product of the contragradient representations, which is just, because these are unitary representations, you can identify essentially with endomorphisms or P phi, let's say a smooth part. And this map is F goes to the corresponding operator. And there you have finally some BH invariant form, which is LH tensor LH bar, where so we had a surjection from Sx to P phi, so the smooth part actually, but right, which was there. And it dualized to a certain H invariant form here. So let me explain. So a priori, it dualized to a morphism between the contragradient of P phi to the contragradient of this, which is the space of all smooth functions on X. But then you can, I mean, this is the same. This is G equivalent by Frobenius reciprocity. This is the same as H invariant linear form, which is obtained by evaluating at 1. And this is LH.
Raphael,
yes?
So why is there two contragradients?
Because, yeah, okay, I forgot to put bars.
Ah, I see. Okay.
It is, yeah, because, yeah, as I said, I don't want to. But yeah, it's because everything is unitary that you can identify.
Yeah. Can I ask also maybe an annoying question? But when you say some representation is unitary, do you include the data of the invariant linear product, or you are saying that exists Of course, it's unique.
No, yeah. It's no. Here I'm
including
including the data of the invariant in a product.
Okay, so you take it as part of the data.
For convenience, right? Which is here. Okay, and so now this series of arrows at the bottom is describing exactly relative characters as in the Pierre-Henry's talk, right? So this is to make the relation. Okay. And last but not least, I would like to discuss this decomposition in the group case again. Where, as I said, the relative characters can be taken to be just traces, essentially, or more accurately, Hilbert-Schmidt scalar products. So it turns out that in this case, so this is for F1 and F2, two functions on the group. Right? In this case, the Plancherel measure is supported not on the full unitary dual, but on a much smaller subset, which is a set of tempered representations. That we know by temp H. So these are irreducible tempered up to isomorphism. And yeah. So as before, you have the Hilbert-Schmidt scalar product, and the measure is I would just denote by mu h because it's canonically associated to the group. So now we, as I said, we have a canonical way to normalize the relative characters, and therefore we have a canonical measure because, as I said, what is canonical a priori in general is only the product, and this is called the Plancherel. And well, in case of local reductive groups, so Harish-Chandra measure, because Harish-Chandra has given a very precise description of it in terms of other data. And I will come back to it this afternoon.
So it doesn't depend on choice of measure on the group, or it does?
No, it does, it does. It does because the L2, but I don't want to talk about measures. But yeah, it does depend on the measure of the group. But here also, it's somehow inversely proportional to the measure on the group. But there is another version of this that will come back later, which is obtained by formally plugging F2 to be the Dirac at 1. It gives you a spectral expansion for F of 1. And there you just get the trace. And a priori, it's true for F in the Schwarz space. But actually, it's not true in general for L2 functions because you cannot evaluate it at one point. But there is a very convenient bigger space here between L2 and the Schwarz space, which is called the Harish-Chandra Schwarz space. That, I will not define precisely, but morally, these are the smooth functions that are L2 plus some, up to logarithmic terms. But yeah, let me, it will be defined in the notes. But there is some natural space there, to which it's like the Schwarz space of the real numbers, to which this formula is, this is the natural space for the Plancherel decomposition somehow. Yes?
So could you explain what's written there? So f of 1, how is that related to the formula of R?
You take f2 to be Dirac at 1. But this is very formal because it's not a smooth function. But when you pair a function with Dirac at 1, you just get f of 1. And Dirac at 1 is like, it's acting like the identity. So here you just get the trace.
Or maybe another way to say f is a convolution of f1 with...
Yes, and then, yeah, that's how you prove it from, properly from there to there, is that actually any function is a convolution product of two functions. And this is just the value at 1 of the convolution product in where you have to conjugate. And okay.
What were we supposed to take away from this commutative diagram?
Is that, so this is a relative character, as I define it. And this is a relative character as was defined in Pierre-Henry's talk. So just to say that these are the same. Okay, so now I can start stating some conjectures.
The first one is invariant under the diagonal action
Yes.
And the second is invariant.
Yes, this one is G invariant, and this one is H times H invariant. Yeah. No. Okay, so now I will state three conjectures. And that are all giving you different, stressing different aspects of the local relative Langlands program. So, and I will start with the conjecture for L2 spaces, which is due to Sakellari and Venkatesh. Since I just introduced decompositions of L2 spaces. So let me state it in two rounds. So first version of the conjecture is this one. So there should exist a natural decomposition of the L2 space of xk as a direct integral over, so I will define the notation in what moment. This form, where, well, so first the parameter space we are integrating over is, this is a set of tempered L parameters. So tempered means that the image of the Val group is bounded on the veiled Ling group to the group of X. So we're using the group of X. And we have to put a measure, or at least a class of measure on it, and it turns out that there's a natural one, and namely it comes from the fact that this set can be naturally written as some disjoint union of quotients of real tori. This is in the Archimedean case, or in non-Archimedean case. But if in the real case you really have to take its tangent space at 1 by a finite group. And this is really comes from the fact that when you have a Langlands parameter, you can always do some enarmified twist in some levy. And this is really describing the family of enarmified twist of a given parameter. And these are taken as the, so. But the point is now that since you have written this way, the set of parameters, there is a natural class of measure. Namely, measures coming from smooth measures on this real smooth manifolds. Yes? Is there a question? So, and this is the measure appearing here, so we'll see this afternoon a better way to normalize it, but for the moment it's sufficient. And last but not least, what are these unitary representations?
So just when you say natural, that just mean something that comes from the Lebesgue measure?
Yes, yes. So smooth measures means Lebesgue measures. So it's yeah, it's coming from, let's say, R measures from there, right? But as I say, the measure is not completely well defined here. You can always multiply by some function. So, but these are the functions which are smooth when you pull back to this corpus on each of these components. So somehow it's the natural measure on family of an ramified twist. And this is multiplicity free. I mean, this is conjectured to be multiplicity free direct sum of elements in some packet. And actually it's going to be R2 packet in general. So that were introduced in Lucas Mazenbaum talk, I guess, 2 days ago. So it's associated to R2 parameter, and let me recall R2 parameter is a morphism on the product of the Veldhening group by SL2. And it's obtained from phi in the following way. So first you can go to Lx times SL2 by phi in the first copy on the Veldhening group and the identity on SL2. And then there is this morphism that I remind you at the beginning between this product and the L group of G. So this is roughly the picture. And this is a parameter. And let me just emphasize that, so I maybe didn't say it or insist sufficiently on this, that the SL2 part of the morphism iota x was depending purely on the parabolic type, px, and that it's a more precise way to say that this parabolic type is controlling the size of the unitary representations appearing in the spectrum of x, because the bigger this SL2, somehow the smaller we expect the representations in the R2 packet. So two remarks right now are that the conjecture is not asserting that this P phi G is non-zero, and actually it might be zero. We will see an example. And we would also like to describe its constituents in terms of some refined version of the local or R2 description of refined description of local L or R2 packets.
But they're disjoint?
No. No, because for example, there are examples where two different parameters phi for x give rise to the same parameter for g, and where actually the same elements in the packet will contribute at two different points. I mean, it's in your work, right? Okay, so let me now discuss another version of the conjecture where at least we'll address the first problem here. And as in Olivier's talks, the answer comes from considering more than one group at the same time. So we saw many versions of this, and I will stick with the simplest one, which is the pure inner forms. So let me define very quickly what are pure inner forms of spaces rather than groups. And so for simplicity, I will have to assume here that G is quasi-split, because we know that. Otherwise, this is not a good notion. And so recall that this Galois cohomology set was parameterizing pure inner forms. And actually, it's parameterizing something else. More naturally, it's parameterizing G torsors that we denote by T alpha. And to such a torsor, we can now associate a new variety, which is so G torsors now, contrary to my previous conventions, G is always acting on the left. And you can take now the contracted product of X with this torsor of a G. And this is a spherical variety for another group, so G alpha, which is the automorphism group of that torsor, which is actually just the pure inner form associated to alpha. Okay, this is a quick definition, and then I will give a concrete way to describe these objects. And then, so the idea will be to consider not just the L2 space of X, but so these are the pure inner forms of X, but the L2 space of X together with all of its pure inner forms. And of course, this is not anymore a priori a representation of G, but this is a representation of the product of all these groups, all the pure inner forms of G, where on each summand only one factor is acting non-trivially. So let me just describe you. So there's a small exercise in Galois cohomology. that I will put as a remark that, okay, you take this, and then you decompose each of these spaces into G alpha k orbits. There might be none, right? So sometimes this is just empty, in which case we say that alpha is not relevant. But doing so, you end up with a description by the first Galois homology set in H rather than G of L2 of G beta k H beta, where G beta is the pure form of G associated to the image of beta in the H1 of G, right? So, exercise. And using this, I can now state a more precise version of the conjecture. So, and we have to assume that G acts faithfully on X, otherwise you caution by the kernel of the action. And again, so this is a conjecture of Sakaris-Venkatesh, and saying that there should exist a natural decomposition of this direct sum of all pure uniforms as before as a direct integral indexed by tempered Langlands parameter valued in the L group of X of some packet where I will not put a superscript G this time because this will contain representations of different pure uniforms. And this is the same measure as before, and the only difference where this time P phi is non-zero. So this is the main difference. So we expect in this case that there is always an element in each of these P phi, multiplicity-free direct sum of elements in the corresponding R2 packet, where I take really the disjoint union over all the pure uniforms of the corresponding R2 packet, and psi as before. So the main difference is just that if you consider all the pure uniforms, you expect all these X packets to be non-zero. Okay, so now let me give an example where we see this phenomena that if you don't consider all pure uniforms, then not all parameters from X will contribute to the spectrum. And this is so-called local Gann-Gross-Prasad conjecture.
Probably the quasi-split form should be included there, right? So you could start, we start from something.
G is quasi-split.
Yeah.
Can I just ask, what is this remark saying, like, if H is trivial?
If H is trivial?
Yeah. Like this.
Which H?
So you have H there, right?
But if H is trivial, it means G is a torus.
Is this only for spherical varieties?
No, it's true everywhere. No, that's true. But if H is trivial, this is just the torsor.
Yeah.
And the torsor are k points only if it's trivial. So this is saying this. Right. A torsor has k points only if it's a trivial torsor. Okay. So this is, and more precisely, I will talk first about strongly tempered varieties and the local Gann-Gross-Prasad conjecture. So definition X is said to be strongly tempered. This is a class of varieties for which actually the Plancherel decomposition can be easily worked out if for all f1 and f2 test functions on H, on X, the matrix coefficient. So you can form a matrix coefficient on G of k, right, by just taking, this is the L2 matrix coefficient, you translate f1 on the right and then pair it with f2 for the L2 scalar product. If it belongs to this, so if it's almost, if it's L2, and actually slightly more than L2 if it's in the Harish-Chandra-Schwarz space of G. So we call it. Okay, it turns out that this is a condition that is relatively easy to check, and it's not always the case. I mean, it's hard. But the point is that now if you have this, you can just plug this matrix coefficient in the Plancherel formula for the group, which I recalled earlier. Is it still on the? No, I erased it. Anyway, there was a version of the Plancherel formula giving you a spectral decomposition of the value at 1 of a function. And if you take the value at 1 of this, you just get a scalar product of f1 and f2. And you can just look at what it gives you, right? On the spectral side, and actually you get something like this. Well, this is the Plancherel measure for G, and this is the relative character, and I will not describe it directly. I will rather describe its dual, like as I said, the relative characters are dual to H invariant forms on linear forms on the representation, or rather on the representation tensor with its contragradient, right? So you have to go back to the picture I drew earlier, but this is dual. It turns out it's easier to describe the dual picture here. It's a map from pi tensor pi bar, let's say, and you take two vectors here, 2c, and just integrate over H the corresponding matrix coefficient. And it's obviously H invariant in both variables. And it's exactly the kind of thing that allows you to describe the relative character as a H times H invariant form on G. H times H distribution, so. Right? Okay. So this formula is a Plancherel formula, which underlies a spectral decomposition for the L2 space, right? You just have to complete with respect to these relative characters. But it turns out that we can describe exactly what's the completion with respect to this relative character because of the following theorem. Yes?
Being told that it always helps to define what you mean by this being equal to that. Remind?
Yeah, so let me call, yes, so we have this map, which is the integral of matrix coefficients over H here. And it's H times H invariant, right? But as we said, so this can be, essentially this is a space of endomorphisms of pi, or if we prefer smooth endomorphisms. And there's a map from S of G there, which is just F maps to pi F. And this gives you a description now of the relative character as like, okay, let me draw the full diagram. So this was the diagram, but as I said, so I'm describing more the bottom line of the diagram I drew earlier, which is describing the relative character as H times H distribution on G. And this is obtained by mapping F to pi of F, and then composing with the integral of matrix coefficient, or if you prefer, you integrating the trace of pi F times pi H. Hope it's... So that's the map I described above, and that's giving you the relative character. Yeah, the relative character is here. And there is this theorem, so of Sakaris and Venkatesh, that in this setting, this integral over matrix coefficient induces.
Sorry, Raphael, I think that what you're.
Yes.
I think that you actually want to put the regular pairing between pi and pi bar there, and the map you're describing is actually the dual of the arrow. You have an arrow from S of G to pi
Yes?
Yes.
Yeah?
Ah, sorry. Okay.
It's fine?
Yeah. Very good.
And okay. So the result of Yanis and Akshay Venkatesh is that this induces actually a perfect pairing on the coinvariant by h. Of course, this will factor through the coinvariance times coinvariance by h bar. So all in all, what you get is that this explicit Plancherel formula gives you a decomposition of L2 of x, okay, as a direct integral indexed by the tempered dual of G. So it's really supported on the tempered dual of G, and actually the measure is the same as the Plancherel measure for G. And there you get pi, when you complete with respect to this relative character, you get, pi, multiple copies of pi, and exactly mx of pi, such copies where mx of pi is just the dimension of the space of H coinvariance. Or if you prefer, this is the space of H invariant linear forms on pi.
What is the this? What does this mean?
This, the previous line. The integral of matrix coefficient.
Oh, okay.
Sorry, yeah. Oh, I was hoping to write this on the same board, but. And okay. So now you see that in this case, in the strongly tempered case, the decomposition of L2 ends up it amounts to describe these multiplicities for pi tempered. And so now I give a very important example, a seminal one, which is a Gross-Prasad conjecture. So in Gross-Prasad setting is you take, so I will describe it for orthogonal groups. So two quadratic spaces over K of consecutive dimensions n and n plus 1. This is an embedding of quadratic spaces. And so the groups are H is a special orthogonal group of the small quadratic space, and G is the product of the two special orthogonal groups. And there you can embed diagonally, right? There is an orthogonal embedding of SOW in SOV. And in this case, X, so G mod H, is strongly tempered. So we are in the previous situation. Okay. And the L group of X is just the L group of G. So it's the product of the L groups of SOW over gamma with SOV. And actually, these L groups can be described, we know what these are. So the dual group of even orthogonal group is just an even orthogonal group. And dual group of odd orthogonal group is a special symplectic group, right? So it's either a product of an orthogonal group with a symplectic group. And this is if, let's see, n equals 2m. Or it's a symplectic group in 2m minus 2 variable times an orthogonal group in 2m variable. And this is if n equals 2m minus 1. So depending if n is odd or even, you get a product in one or the other order. But in all cases, these are products of orthogonal group by a symplectic group. Okay, so in this case, I will now describe you what are the behavior of these multiplicities in packets. And you will see that if you don't consider all pure inner forms, then sometimes the multiplicity is just 0 over a full tempered packet. So let phi v and phi w be tempered Langlands parameters for SOV and SOW. And we consider the corresponding packets. And actually using these descriptions, we can naturally embed each of these dual group into a general linear group of a complex vector space that I will call M and N. Okay? And we'll see them as representations of the Veil-Dealing groups that are either orthogonal or symplectic. Okay. And now I recall a version of the local Langlands correspondence. So as stated in Olivier's lectures using pure inner forms. So let's see. Let me do it for V first. So you have to take disjoint union of the packets. So I mean, this is the refined local Langlands correspondence. So we are now going to parameterize elements in the packet. So you have to take pure inner forms, which are parameterized by the scalar cohomology set. And actually, this parameterizes more naturally quadratic spaces that I would call V alpha of the same dimension and discriminant as V, because this is exactly the automorphism group of that. And then the corresponding pure inner form is just the special orthogonal group again, but of V alpha. And so the refined local Langlands correspondence tells you that this should be in bijection with a character group of a certain finite group, S phi V hat. So this is a character group, where S phi V is just the component group of the centralizer of phi V in the dual group. This is very rough reminder on what the refined local Langlands correspondence is saying. And of course, you have the same for SOW. So with obvious notation. So now beta is parameterizing quadratic spaces of the same dimension discriminant as W. And this is the component group of the centralizer of phi V, phi W. So. Okay, so I have almost everything to state the theorem. Except that still need to describe the pure inner forms of X rather than the groups. But these are easy, right? Because, as I said, these are essentially parameterized by the scalar cohomology set in the subgroup, actually. And if you want to describe orbits. And this gives rise, as before, to quadratic space W beta, but also to quadratic space V beta, because you can always consider the image of this in. And this is actually, there's a map in SOV. Right? And this is included there. And actually, so it's easy to describe in terms of W beta. This is W beta orthogonal direct sum with a certain line, which is given from the original pair we started with. So L is the orthogonal complement of W in V. Right? And now, so for each beta, you get a new pair of quadratic spaces as before. And so you can construct a pair of group also, similarly. And you also have a multiplicity. In this case, I mean, X beta is just the quotient. And for pi in irreducible representation of G beta, you can define this multiplicity. Okay, so now theorem. So this is proved by Valspurger and formerly known as the local Rose-Prasad conjecture. Okay, so assume, I already said it, but let me say it again. The parameters are tempered. Then there exists a unique representation in the corresponding packets where we run over all pure inner forms of the space, right? So pi belongs to, take not all pure inner forms of the group because some will not give you pure inner forms of the space. There will be no points. So these are parameterized by those beta as before, and then you have the packet for, let's see, these are just product of packets for the two special orthogonal groups, right? And so this is a tensor product because representations in the packet for the product of the two special orthogonal groups are just tensor product of representations in these two packets. And so we'll write accordingly pi as a tensor product of two irreducible representations sigma prime sigma. And there is a unique such pi with the property that the multiplicity of pi is 1 and the multiplicity of the other representations are 0. So this is already saying that, I mean, since there is more than one pure inner form, if you just consider one space, one of those spaces, x beta, sometimes the packet will not contribute at all. And moreover, we can describe precisely what is this representation. Namely, we can describe, sorry.
So what's the end of the sentence? 1 or?
Okay. Two sentences.
Pi?
Maybe you will write pi
The
pi.
multiplicity.
So there is a unique pi whose multiplicity is 1. Sorry, yeah. Okay, so sorry for being lazy. Moreover, the multiplicity is 0 for all the pi prime in the packet. And okay, and so this sigma and sigma prime now, they correspond to characters of the component groups. And recall that, so in Olivier lecture, it was denoted by this, or I don't remember if sigma was on the left or on the right. But so this is, so the point is that furthermore, we can describe this character. So this is a character of SV, V, and we take an element in SVV. And the pairing with S is given by the following formula. So it's essentially a root number, local root number, times some value of central characters. So let me define all the terms here. So recall that phi V and phi W are parameters, Langlands parameters for SOV and SOW. So this is upstairs, I mean, on the top here. But we are seeing them as representations of the Veldin group on two complex vector spaces M and N. So these are the M and N here. S is in SVV, but we can lift it to an element in the centralizer of VV, right? And this is what you are doing here. M minus S is just, I mean, S is, this is S in particular, if we lift it, it's acting on the space M. And this is the -1 eigenspace for S, which is again a representation of the Veldin group, because it's commuting with the Veldin action. And that's it. Right, this defines all the terms. This is the local root number of the tensor product of these two representations of the Veldin group, and these are the determinants at -1. And one point is that this actually, also this depends on the choice of the lift, right? The expression here doesn't. And there is a similar formula for the character of the component group associated to sigma prime. But I will not write it.
So Raphaël, there has to be an identity character in the basis somewhere?
No. No, because this is even dimensional. Both are even dimensional. I mean, divided by 2. And the one is orthogonal, the other symplectic. When the tensor product, the central character is trivial. The determinant is trivial. So it doesn't depend on the choice of the additive character, but of course, this parameterization that do depend on the choice of a Whittaker model. I didn't. Well, I don't know.
But where is that?
Because it doesn't depend on psi. Actually, it depends on some other data that you can fix from the data of L. And the point is that when you have a generic character, so it's only even orthogonal groups. There's a different Whittaker data. But when you multiply a generic character by a scalar, you can see that it's always conjugated to the original one, rationally. So the difference is, but yeah.
Sorry, so you're saying that the data of your problem will give you a way to choose?
Yes, so the data of my problem, so this L more precisely will give me a way to normalize these bijections, so the one for the even orthogonal group. And this is why we don't see extra data.
And where can we read about that?
It's in the paper of Prasad, everything is defined, and they show that it does not depend on the choices, and that, yeah. But the reference is in the notes. But, okay, how much time? Okay, very late. So I will state one last conjecture then, I guess, and okay. So this is the second conjecture. And let me give you a third one to give you. So this is remark that this is at the same time more special than the previous conjecture of Zacharias and Venkatesh, but it's also much more precise, right? And now we will state another conjecture in some special cases that are again more precise than the general conjecture of Zacharias and Venkatesh. And then if someone can come up with a general statement specializing to all three, then it would be very nice. So this conjecture is a conjecture that has appeared in recent years, as due to Prasad. And it has to do with a situation, I mean, it's very close to the group case, but it's slightly twisted. So more precisely, we will twist it by a quadratic extension. So let H be, so I will take it to be quasi-split to simplify, and I will take L to be a quadratic extension of K. And so the group, I mean, this is a subgroup H, and the big group will be just H over L, but we have to take restriction of scalars if you want to make things properly. And X is, of course, G mod H. So the point is that over the algebraic closure, this becomes isomorphic to the group variety, right? So this is really, the dual group is the same as the dual group for the group. But the point is that now we have to be careful with the Galois action, right? So let me describe for you the dual picture. So what is Lx in this case? Well, the neutral component is the dual group of H, of course. And then you have a Galois action. And there's a natural Galois action, pin Galois action on H hat, which would give you the L group of H, but this is not what you get. You have to twist it somehow by this Chovale automorphism I talked at the beginning. And then it's mapping to the L group of G, which is so H hat times H hat. And again, there's a natural action of Galois, which is coming from the Galois action on H hat, and you have to twist it by some switching, I mean swapping automorphism. So let me describe more precisely what I mean by this, where the actions, so the gamma actions are twisted by one cocycle, which is going from gamma to, so it's actually factoring through the Galois group of the extension to the automorphisms of H hat, and it's sending the non-trivial element there that we call sigma, so of H hat or of G hat, sorry, depending whether you are looking here or here. In the first case, you have to twist it by the one cocycle sending the non-trivial element here to the Chovale automorphisms, C. And the second case to iota, which is just switching the two copies. And you can check that, yeah, this, and the map is the same as before on neutral components. Okay. So now let me introduce some notations. So phi G will be the set of L parameters for G. Okay, and as always, we consider them up to G conjugacy, G hat conjugacy. So. And we can do the same formally for X, right? And this is iota X, sorry. And taken this time up to X hat conjugation. And we have a natural map from phi X to phi G, which is just the push forward by this morphism. Right, so it's sending so phi prime to, so we call iota X star, lower star maybe, to iota X composed with phi prime, so called phi. And turns out that these are actually not just sets. You can undo them with, so these are naturally algebraic varieties over C. So again, essentially you take all Langlands parameters and there is a natural structure of algebraic varieties by looking at families of unramified twist, and then you take the GIT quotients. So it's really the most naive way of defining a structure of variety on set of L parameters. So GIT quotient. And for those structures, this is a morphism which is finite. And so let me state conjecture of Prasad now. We'll use this one. So in some sense, okay. This is, so Prasad has a much more refined conjecture, and here I will not try to state it, I will just state a stable version in some sense. Just to give you an idea. So it works for any parameter that is tempered, for example, or you can even put a much less restrictive assumption that is generic. So generic means that it should contain the corresponding package should contain a generic representation, or conjecturally it's the same as saying that the local adjoint L factor has no pole at 1. And then, okay, so why stable version means because you will sum over the full packet. What did I define the packet? Did I define the packet? So, tuck. So the packet, sorry, I should have defined the packet, is really the union of all pure inner forms. I mean, I'm again taking Vaughan extended L packets for pure inner forms. And so I sum over the packet. And for each element in the packet, you have a character of the component group as before. And we are just taking the value at 1, that is the dimension of the corresponding irreducible representation, times the multiplicity of x at pi. So more precisely, if pi is living here, you have a corresponding pure inner form as before. And mx of pi is the dimension of the Helm space G alpha from pi to the space of all smooth functions on X alpha. Right? So it's the same multiplicity as before. And okay, so this is the stable multiplicity in some sense. This is equal, or this should be equal to the sum over the fibers. So now we are going to see this, that so sometimes the fibers are non-trivial. And I will give an example in one moment. And so we are summing over the fibers of that map. And a certain thing, so first we have to take the component group of the centralizer of phi, but modulo the centralizer of phi prime, which is naturally included in the centralizer of phi, times a term which is important, which is, so more or less you would like this to be constant when you vary the parameter. There's some reason to believe this. And if you do this, the problem is that this is finite, but this has some ramification points. And so the size of the fibers can shrink. And so you have to count elements in a fiber with their degree. So the degree of this at phi prime. And this will give you the stable multiplicity. So before giving you one example, I think we still have 3 minutes, let me give as a remark that it is known in some cases. So for H equals GLN, first of all, for GLN it's not, okay, it's interesting already, but you don't see really all these phenomena. I mean, namely the fibers are always of cardinality at most 1, and multiplicity are at most 1, so there is no, you don't see all this stuff coming. So this is due to cable matrage, I think. Then you can deduce the same for SLN. Stable version is easy. Then for unitary groups associated to this quadratic extension, this comes from the work of Fagan, Lapid, and Offen, following previous investigations by Jacquet. And there, in this case, yeah, you do see large fibers and ramification points. So I will give one example. And then for GSP4 and some other, I think SP4 and SP4, this was checked by Eng-Fei Lu. Okay, and I think this is all I know. Maybe there are other cases, but I'm not aware of. And let me end by just giving you one example. So this example is H is so it's PGL2. So in this case, iota x star is going from the set of L parameters it's just the base change map for L parameters for PGL2 over K to L parameters for PGL2 over L, right? So parameter phi prime, you associate just this restriction. So it's a morphism in SL2. SL2 is the group of PGL2. It's restriction to the Veil-Delin group of L. And just look at the unramified parameters. I mean, or the principal series, let's say. So a parameter of a principal series here is a direct sum of chi prime and its inverse, right? Because it has to go into the maximal torus for SL2. And then its restriction is just the same, where chi is just the restriction of chi prime to the Veil group of L, or if you prefer, you're using class field theory and thinking of them as characters of multiplicative groups, it's just composition with the norm. Okay. And what are the fibers when you just look at the map between the principal series? Well, you see that, 1 minute. So for chi in generic position and in the image, so so in the image means that chi sigma equals chi inverse. No, equals chi. And so for chi, so the fiber is fiber has 2 elements. This chi prime, 1 element in the fiber, and the other element is obtained by multiplying by the quadratic character associated to this extension, which of course will give you the same restriction. Sigma, sorry, is the non-trivial element in the Galois group, as before. But if sometimes, I mean, you have to these are not just spaces of characters because you have to divide by conjugacy, so that is by the action of the Veil group. So you cannot distinguish between chi prime and chi prime inverse in the space of Langlands parameters. So if this is just equals to chi prime inverse, which happens precisely when -1 is a norm. So for example, if L over K is unramified, the fiber is of cardinality 1. So, but in this case, the multiplicity is generically 2 and still 2 in this case, even if the fiber is of cardinality 1. So let me just, end with, okay, it's a very rough picture. So this is the picture, right? So for generic chi, you have 2 elements there. But at a point where chi prime square equals eta L over k, you have just 1 point. And of course, it's of degree 2. So, and if you look at the same situation for unitary groups, but in higher rank, you have exactly the same kind of phenomena, but slightly in higher dimension. And it turns out that indeed, if you don't put the degrees here, it turns out to be false. So, and this is the result of Fagon mapping. You prove that it's at least this, yes. You prove that it's at least this, yes. Yeah, and then, okay, but okay. I stop there. Thank you.
Any questions?
Raphaël? Yeah, please.
So if I understand correctly, non-tempered representations of G can show up in the spherical spectrum, like with L2.
Yes, so it's expected that, no, okay. The conjecture of Sakalis Venkatesh is telling you that we could expect non-tempered representations when the SL2 part of the embedding is non-trivial, which means when the parabolic type Px is not B. And actually, you can easily come up with some non-tempered representation in the spectrum. So that was the last topic I didn't have time to discuss, but we can describe the most continuous part of the spectrum quite explicitly as induced from this parabolic Px of characters. And when Px is not B, these are indeed non-tempered representations.
Are there other questions?
Is there a L-square version of precise conjecture, like similar to the circularity spin function conjecture? I mean, predicts the decomposition of the L-square space.
Yeah, but I guess yes, but it's not.
It's a special case of the circularity Venkatesh.
Yeah, but you can also describe explicitly what is in the packets, maybe, or how many elements you have in the different X packets. But yeah, it should certainly be that all the. It's known that mostly known that all tempered pi, the multiplicity, smooth multiplicity is the same as the tempered multiplicity in some sense. So.
Yes.
So, why is the generic important?
Because okay, that one issue is that so you can think of tempered instead of generic, but because basically generic or representations generic packets can be obtained by holomorphic continuation from tempered representations because it's always isomorphic to their standard modulus, or at least conjecturally. But for the non-generic ones are the ones where you, it's like elements in R2 packets where you have a non-trivial SL2. It's there's no conjecture yet. It's okay. This should be thought as a conjecture for the most tempered part of the spectrum. Maybe.
Yes, let's have one last question.
Okay. So your shoe case, local field current is 0, right?
Yes.
But some results are also known for class P. For example, the first conjecture is you say that if sigma 2 is the dual of sigma 1, then the our packet is.
Yes, that was proved by one more. Yes, I forgot to mention. Yeah, sorry.
I wonder why your shoe case current 0.
It was just for convenience. But for example, Valls-Piaget theorem is only proving characteristic 0, and I think in the book of Sakalis Venkatesh, I assume characteristic 0 to use some compactification theory that is not. I'm not sure it's entirely, but yeah, it's technical.
Yanis would like to formulate a question because he has to go off shortly, so he will not join us for Q&A, but he would like to formulate a question for the Q&A. Now, okay, please.
Use the mic. So why is the stable multiplicity
bigger than 1 here, and it is 1 for gross Beuzart. Is there a conceptual way to understand it?
Yeah, this is the, I mean, basically it has to do with the cardinality of fibers. So in the gross Beuzart case, the dual group is the same as the dual group of G, so these fibers are just trivial. And here you have to take this into account, so it's kind of fiber of the stack quotient.
Okay, so we reconvene at 10:40.